Hello there, welcome back to day 2. Well, technically it's day 3 for me. Same as the last one, I'm gonna walk you through my thought process about my first look on today's LeetCode problem. Let's begin. Oh, we got a medium today again. Associated. So we have an array called stones I, value of the ith stone. Oh, it's not a game theory, I think. The player remove any stone from stones. Oh, what? That's a strange rule. Alice and Bob should find another game other than playing with stones. Play optimally, return true, okay, classic. The rule is strange though. Okay, I'm gonna get out paint here. Okay, I'm gonna think about this. So, with LeetCode's medium problems or any problems in general that, well, doesn't follow exact data structures theory or something, it's mostly just finding out a pattern. And noticing it can dramatically make it easier. So I should start asking questions like, is it possible that they can always clean up the entire board, you know? Which I think is already impossible, because for example you have 3 values x, y, z, and let's say Alice can pick y, and if x plus y is divisible by 3 and y plus z is divisible by 3, then Bob Bob just loses here. So that theory is out the window. Okay, what's next? Another thing that I would notice is I can actually simplify this down to just 3 values that matter. I can mod all of this by 3 to get values ranging from 0 to 2 because those are the only values that matter alongside with how many there are. So 5, 1, 2, 4, 3, let's take that as an example. So we would get 2, 1, 2, 1, and 0. Okay, so now since the order these are the numbers are placed doesn't matter at all, I can manage this with just an array or 3 variables. I'll call this count. I just write C for short. So C3 is going to store the counts of all of this, which is gonna be, there's 1 0 and 2 1s and 2 2s, so it's gonna look like this. Now next is asking, okay, let's say, so we have 1 and 2 and 2 here. Now what I noticed is, what I found out actually is, okay, what I noticed is there are only 2 states the sum can be. It's either divisible by 1 or it's divisible by 2, because it can't be divisible by 0 or, no, wait, no, okay, I phrased that wrong, sorry. It's either, okay, so if you take the sum and you mod it by 3, it's either going to be 1 or 2. It's not going to be 0. So if it's on 1, whoever turn is currently, they will need to pick 1, because if they pick 2, the sum will become 0 and they will lose. So they will have to pick 1, which will switch the state to 2, and if it's on 2, similarly then we can only pick 2, which flips the state back. So okay, so for to make this a bit easier, I'm going to just try to ignore the 0 here and let Alice and Bob play purely on 1s and 2 because that's what I'm thinking of right now. So let's say there are 3 1s and 2 2s. If Alice goes first and she picks the 1, then it's gonna become 2 2. So it's A B A B blah blah blah. Alright, so Alice picks that. So now the sum is divisible the sum will have a remainder of 1 when divided by 3, which means Bob will also need to pick this. So the turn, it will become 1 and 2. Alice will pick 2, which is gonna be 1 and 1. Bob picks this, which drops it down to 0 and 1. And Alice picks this, which reduces it down to 0 and 0. So it's more like okay. Okay, so whichever value Alice picks first, I can imagine that as Bob is gonna play in that group for the rest of the game, and Alice is gonna be in the other group. You get what I mean? Like if Alice picks group 1, then for the rest of the game, Alice will be only taking numbers from group 2, and Bob will be taking from group 1. So I can ditch this first turn, and the actual game starts here with Bob and Alice just keep taking until one of them runs out, and Bob will make the first turn. Bob will make the first move. So if Bob makes the first move, that means if Bob's group, I'm just gonna call it CB, Bob's group is less than or equal to Alice's group, then Alice wins. Then Alice will win. Okay, I think. I can try testifying this. Oh no. Yeah, I think it's pretty clear that this is gonna be how it's gonna be. Is it though? Okay, so CA. Let's say this is 1, then it's gonna be Bob go first, 1 1, 1 0, and then 0 0, and Alice loses. Okay, so I'm gonna rephrase this a little, or actually I'm just gonna yeah, I keep it like this. That works. So yeah, I'm gonna zoom in a little bit. If CA is larger than or equal to CB, or I'm just gonna use that, yeah, then I'll put A, or A wins, yeah, or else B wins. Now the next problem is, wait, not yet. So if Alice goes first, then it's gonna be pretty clear that she's going to pick the group that has the less counts in it, because she will switch to the other one. So for example, if C1 is if C1 has like 4 in it and C2 has 5, it's obvious that Alice is going to pick C1 to go first, because then Bob is going to be locked at C1 for the rest of the game, and Alice can use numbers from group 2, which is clearly more than group 1. So that's how Alice is going to win. So Alice is going to win if, okay, yeah, basically Alice is just going to win all of that, I guess. Wait, can Alice lose? Actually, can Alice lose? Okay, what if they're equal? Like there are 4 C1 and 4 C2. Then Alice picks this, which the game starts with 3 and 4, and Bob's stuck with this, and Bob loses. Yeah, I think Alice can always win if it's just 1 and 2. Now for the zeros. I'm trying to figure out how to insert the zeros into this. So 0 is so you know how I said that Alice is gonna be locked in one group while Bob is gonna be locked in the other group. When we introduce 0, you can imagine it like A's and Alice's group and Bob's group swaps. So let's say Alice is playing on group 1 and Bob is playing on group 2. If one of them picks a 0, then they swap like this. Should that matter? I feel like the positions of the zeros shouldn't matter, because then it would be a problem too hard for medium. I'm basing this off of the difficulty, which might be not a good idea, but I'm just gonna go with it. So let's say Alice and Bob finishes the game with this. Now one of them runs out, so the other one starts using zeros. So 0 is going to swap their, like I can say the amount of numbers they have. Oh yeah, that shouldn't matter. It shouldn't matter where you place 0, because if you place a 0, like if one of them plays a 0 at, let's say this is the entire game timeline, if one of them plays a 0 at this point and they swap, if they play a 0 again at another timeline, they just swap back again. And this is gonna be the same even if they play two zeros over here. And it's gonna be the same if they place 2 zeros anywhere. That's what I think. So I might as well I can probably figure out which group A is gonna land on based on the 0, the amount of zeros. So let's say there are 3 zeros. I'm gonna introduce a third column here. Let's say there. Okay, let's start with 2. Alice will start by playing C1, which brings this down to C2, 2, 3, 4. Let's say Bob plays a 0. And then this will be Alice's group. And then this will be Alice's group, and this is Bob's group now. So like this is now B. This is now A. And if they play again, they're gonna end up with the same group. Okay. I just oh wait, actually I think my claim earlier that Alice can just win, can always win if they're just 1 and 2 is actually wrong. Because you can see this here. Bob will always win. 1, 2, 3, 4, 5. Oh, right. Yeah, so I think I missed a crucial part. So the game doesn't end when one of you run out of things to place down. Okay, so let's simulate this game right here and how Bob wins this. I think I already did and it was faulty, I think. So let's say Alice chooses this, which is the greedy method we talked about earlier. So Alice's group is going to be over here and Bob's going to be over here. Now the group, it's divisible by, the remainder is currently 1. So Bob's gonna play this, which drops it down to 1 and 2. Now Alice can, no, it's not this. Oh wait, it's 2, 2. Okay, this is kinda, God, I'm losing track here. Okay, let's start over. So we just 1 and 2. And maybe a 0 as well. Let's say there's, okay, 1, 2, 2. Alice picks this, so she'll go over here, drops this down to 1, 1, and 2. Now Bob plays this group. He also has to pick something from the 1 group, which is going to be 1, 0, 2. Now Alice will not play a 0, because if she plays a 0, then the resources, or like how many numbers they have, will swap, and they will Alice will end up with a number that is on this side of, which is just less. So she plays this. Now Bob can play a 0 because he's gonna lose if he played a 1, so this is gonna be 0, 0, 1. Now Alice is over here now, Bob's over here. And Alice doesn't have anything else to play. So Bob wins. Okay. Okay. I mean I can simulate this. I could. But I feel like I can calculate this in just one line. Okay, I'm just gonna quickly count all of this. I'm gonna use an array. Since he stones, I then mod3 increment. Okay, so now I have to count. Can Alice know how many times this will swap? So if this is 2, Alice's group will stay the same throughout. If it's odd, Alice's group will swap by the end of the game. Okay, so there's this this thing here we talked about earlier. If this is true, like there's no 0, Alice can always guarantee a win. But since they can swap, and so Alice will only lose if C1 equals C2 and the number of count 0 is odd. That's what I'm thinking, and I'm gonna implement it. So if equals 2 and count 0 is odd, yeah, it's odd, return false, or else return true. Is this it? No, I don't think this is it. Hold on. Oh, I just realized there could be an edge case where there's just one stone, a bunch of stones with the value 0. In which case Alice would lose immediately, and I'm just gonna count 0 equals stones.size, return false as well. Okay, I think this is it. And I run the test case. Oh, I got wrong answer actually. So there's just one stone. What? Alice loses this? Oh, what? Oh, Bob will win automatically if there are no remaining stones. Okay. Okay. I missed that part. So how can I change this? I really don't want to simulate this. I don't want to create another function where it just runs through the game. Like, there's only two cases. Either Alice starts on C1 or Alice starts on C2, that's it. And everything else after is deterministic. Wait, this is a very strange rule. Why? That's so unfair. I mean, yeah, Alice goes first. Okay, I guess that's fair. Oh my god. How do I know if the game can reach, like they can, Okay, I don't know if this is correct. Count 1 equals count 2. If Alice takes... Okay, so this is a case where... they're different. So if Alice takes the group 1... Okay, imagine there's like 1, 0 in here. If Alice takes group 1, then it's gonna be 2, 2. And then Bob takes a 0. So now Alice goes first and it is swapped. So Alice will lose this actually. So it's more like... So it has to be 1 higher? Okay, so CA plus 1. So this is... Okay, what if it starts with 2? Then yeah, okay, Alice loses. We already know that outcome. Yeah, I think I'm just gonna implement the I'm just gonna simulate now. So try. Let's say this is where it starts. Alice's first choices. And then I'm gonna run through. How many stones there are as well. So wow, size minus whose turn is it? So it's Alice's turn first. If the current sum as well. If sum equals 0. Okay, hold on. Sum equals st actually. And they already picked one number. Turn equals false. So now it's Bob's turn. Okay, this is not a good way to start this. How can I even simulate this? Okay, you guys start with sum 0. Current equals true. If I equals 1. So if it's the first turn, I'll take care of this separately. If they actually go through all that and the sum is not divisible by 3, return false. And then sum equals try. This is gonna be a starting value. I should move this down here. Sum equals size, and then turn equals not turn. Continue. Now, or else, if the sum is 1, then they would take either from count 0 or count 2. If count 0 is still larger than... Yeah, I should also... Because that is also a global variable and I need to run this multiple times. It's not hard, it's just so annoying to implement. So if count 0 or C0 is larger than 0, then they will always take that because it doesn't matter when they take that. Turn equals not turn, continue. If sum equals 1 and if count, they will have to pick a 1. It's larger than 0. Then they safely pass. So turn equals not turn. Else return whoever turn it is, or return not turn, so the other guy wins. Else sum, basically the same, but this time it checks for count 2. Yeah, I kinda don't like this implementation, but I'm gonna see if it works, which probably would. Now Alice goes first, so of course, she would try to find the start that can guarantee her a win. So she's gonna try starting from, okay, bool winner equals false if count 1 is larger than 0, which means there exists a number from group 1. Then we'll try 1 size is stones dot size, and the other is basically the same but trying for group 2, and winner would take, well, whatever that returns true. So it's gonna orbit off that, and we return winner. Yeah, not the best solution, I would say, but I'm gonna see if it works. Case 1 returns false. Okay, I'm gonna see how this runs. So Alice tries 1. Turn equals true, and they go through the stones. If it's the first turn, then sum equals the first number. Turn, oh right, I haven't decreased this. C0, go down. C1, decrement. C2, decrement. I think that's the problem. Oh wow, now this is the problem. Okay, so turn. I'm gonna output, I'm gonna try debugging this. So first I'm gonna print out whoever turn it is, and then I'm gonna print out how many numbers of each are there left. Okay, it's trying 1 first. And for some reason there is, oh, this just becomes 0. It's supposed to be 1, 1 and 1. Continue. If sum equals 1. Oh, I haven't switched that yet. So if this is sum equals 1, now sum equals 2. Now sum equals, I should name that to remainder, but you know what, that works. I think that's the problem. Yeah, now it works. Comment this out. Oh my god, I think that took longer than I wanted to. For a medium problem. Hold on, I'm gonna see if this actually runs correctly. Oh, I got accepted. Okay, yeah. I actually, that did better than I thought. Beat 62%, I'll accept that. So since I'm done, I'm gonna go look at the other solutions to see if anyone actually managed to like do all of this calculation in one line and not having to make a helper function like this to try running through 2 of the, yeah, something like this. I wanted to do something like this. Bool equals frequency in 1. So it's checking if 0 is odd or not. So if it's even, then it's going to return this. It's even, then it's going to return. Oh yeah, so if it's even, then it's going to go back to Alice can just win in any case, actually, as long as they're these numbers. Okay, interesting problem. I didn't like that though. I didn't like this problem though. No, I don't really like this. It's yeah, there are better problems to practice on. This is not my taste. But yeah, that is day 2. Thank you guys for watching. I'll catch you guys tomorrow.